Okay, in this video we're going to be taking a look at the speed of light in a medium and how to characterize that. And I figured I would start by reviewing a point from when we studied waves in mechanics. So you can see I have a question up on the screen already. What I would like for you to do is pause the video, think of what response would be correct, and then we'll discuss that on the other side of the pause. Okay, it turns out that the correct answer is choice 1, only the wavelength changes. So the best explanation that I can think of for that was what I've been told some time ago. So imagine a tale of an incredibly well-organized jailbreak. So over here we have a jail. And we'll stick in our barbed wire fence here. Yeah, that's supposed to be a barbed wire fence. Oh well. We stick in our barbed wire fence there. And we imagine that the prisoners in the jail have discovered a flaw in the security systems. And it allows them to escape one at a time, once a minute. So once a minute, we can somehow get a prisoner from one side of the jail over, oops, over to the other side of the jail. So it's happening once per minute. Now, what we can imagine is at first, and they're escaping from the jail, on the other side of the fence is a road, standard hardtop road. Now you could imagine that they could run pretty quick down that road. So if we look at where, say, this prisoner gets 1 minute later, they'll be over here. All right. Now for the next stretch of it, imagine that they have to, in order to avoid capture, they have to run off the road and over into a grassy area. Well, you can't run as fast on grass as you can on asphalt, right? So a minute later, maybe they've only traveled that far. And then another minute later, say they're over here. Then finally, let me touch that up just a little bit. And then finally, they get over to some swamp. Now you can't run very fast through swamp at all. So the distance our prisoner would cover in minute by minute would be rather short. So now the question is let's assume that there is a SWAT team at the other end capturing the prisoners. At what rate do they capture the prisoners? 1 a minute. You can't capture them any faster than 1 a minute. If you did, then we would be running out of prisoners. If you captured them slower than 1 a minute, you would be creating a traffic jam of prisoners. So you can only catch the prisoners as fast as you make them, which is 1 a minute. So the frequency stays the same. The wavelength changes. We can see the spacing between the prisoners changes. So let's do an example of that in the context of light. So let's say you were listening to the radio station CIMX. It broadcasts at a frequency, oops, sorry about that. It broadcasts at a frequency of 88.7 megahertz. And we would like to know, what is the wavelength of this radio wave? Well, it's still the case that the speed of a wave is equal to the frequency times the wavelength. Here we write c for the speed of light in a vacuum. And technically the speed of light in air is just slightly less. Unless you're a professional astronomer, you don't usually care about that. But we can say the speed of light is equal to frequency times the wavelength. So the wavelength will be the speed of light over the frequency. So the speed of light, whoops, sorry about all that. The speed of light is 3 times 10 to the 8 meters per second. And our frequency is 88.7 times 10 to the 6 hertz. Now hertz is the same difference as 1 over seconds, so hertz and 1 over seconds cancel to leave us with meters. And it turns out that this wavelength is 3.38 meters. Now we should ask ourselves, is this a reasonable wavelength? And the answer is yes. Keep in mind, we've seen before that in order to transmit or detect an electromagnetic wave, the antenna has to be roughly the same size as the wave it's picking up. And by roughly, I mean like within a factor of 100, or even if you push it 1,000. So if you think about the width of a standard car radio slot, standard car radio slot is about about 20-25 centimeters wide, something like that. So that width is compatible with an FM antenna that would be seeking to pick up wavelengths that are a little more than 10 times longer than that width. So in part, the width of the radio slot in the car is chosen in order to fit the antenna. So this gives us some confidence about it. All right, now I've already mentioned or alluded that the speed of light in a medium is not the same as the speed of light in a vacuum. So I've already alluded to the notion that the speed of light in a medium is not necessarily the same as the speed of light in a vacuum. In fact, it will always be slower. One way that we can see that is we saw that the speed of light in a vacuum was 1 over the square root of epsilon naught mu naught. Now, if we're in a medium, it turns out that you'll need to replace the epsilon naught with epsilon for the medium, mu naught for mu in the medium. And when you do, the result that you get will always be slower than the speed of light in a vacuum. So the speed of light in a medium, we'll call that v, that will always be less than the speed of light in a vacuum. Now in the case of some media like air, it turns out that the difference is less than a fraction of a percent, is a small fraction of a percent. And so it's not really a big deal to worry about unless you're a professional astronomer or something. But if, say, you're talking about glass or something like that, well, then that's a big deal. Now, it turns out that most of the time what we're worried about is how this is going to be changing the wavelength of the light. So we define a quantity called the index of refraction. For light. So for a material. So the index of refraction is defined as the speed of light in a vacuum over the speed of light in the material in question. And this will be a number that's always bigger than 1. So what does that mean for us? Well, if we remember that we said that the speed of a wave is equal to frequency times the wavelength. If the light wave goes from one medium to another, the frequency stays a constant. If the speed of the in the medium goes down, then so does the wavelength. And how much is it going down by? It's going down by a factor of n. So this means that if light enters some material, the wavelength will get shorter. So the wavelength in a material will be equal to the wavelength in a vacuum over this index of refraction. Now the index of refraction does not have any units. You can see that because the speed of light is meters per second, and the speed of light in the medium is meters per second. So it's just a number. And the slower light goes through a material, the shorter the corresponding wavelengths of light will be for the same source. And the slower light will go through. For materials like glass, the typical index of refraction would be on the order of about 4/3. For water, it's something like 3/2. For diamond, it's 2.42. So say if I have light that is traveling from air into, let's say, glass. So here the index is basically 1. We'll just say it's 1. Glass is roughly 3/2. So we'll just say it's 3/2. So here we would expect the wavelength to be 2/3 what it was before. So if this is my wavelength here, as my light is propagating in, when it goes into the glass, it's just like the prisoners packing up. It scrunches up, and so this should be roughly, this peak-to-peak distance here, should be about 2/3 what it was in air, except I didn't do a very good job of drawing it. Okay, I will catch you in the next one.